In the previous section, we have finally established the notion of the differential of a map, and so defined the general notion of differentiation of maps. Now, in this section, we want to take it a bit more concrete, namely we want to establish some rules for differentiation which allow us to explicitly compute differentials. Same as before in Mathematics 1, if you recall, we have defined the derivative by differential quotients, but almost never used really explicit differential quotients of a function to really compute the derivative of a map. Instead, we have used this notion, so this differential quotient, to establish some derivatives of some very elementary functions, and then saw that if we kind of collect all these functions together, or if we compose them, or take products, and so on, everything will be differentiable, and we can take the derivative by the product rule, chain rule, and so on, if we know the derivatives of some explicit elementary functions, and then we can derive everything. And it's similar in the multidimensional case. There's also a product rule, a chain rule that we will see in this section, and some further rules. So we will again not really often use the explicit notion, the explicit definition of the differential, but instead use more convenient computational rules instead. And as we've seen, the partial derivatives that occur in these differentials can be computed by standard methods, so by one-dimensional derivatives. So we can basically transfer the old notions and use them also to compute derivatives, differentials of higher dimensional maps. Okay, just to recall, I've written down here the shorthand version of the definition of the differential. So a map f from U to Rm, where U is a subset of Rn for some n and n, m and n are arbitrary here. It's differentiable in the point A in U if there is some linear map, and linear is important here, which we call dfa, which has the following property: f of a plus h, so a plus a small perturbation, so to say, a plus h is f of a plus dfa in h. So plus something, plus some, which I often call just rubbish, or just something small. And something small means this fulfills this limit here, which means this is something which is smaller than linear, very roughly. So the interpretation was that this here means that this linear map, dfa, this is a map, this is the best approximation of f in this point A by a linear map. Okay, so this is what we've seen. So the best approximation of the map by a linear map. Now, the first result that we want to study is a kind of sanity check. Because if this notion of linear approximation works, we should also know the answer to the following. So Theorem 1222. So let's take m and n in n, and now let L, I call the map now L, from Rn to Rm be a linear map. We already know that every linear map from Rn to Rm is continuous. This is what we've seen in the previous chapter. But now, come to think of it, so the differential is the best approximation by a linear map. And if it's differentiable, a function with or a map, this means that actually we can approximate by a linear map. So this somehow makes sense. Now, if we already have a linear map and we are searching for the best linear approximation of a linear map, what should this be? The map itself. I mean, this is the map, so you can't have a better approximation than that. So we would expect it is differentiable, and the differential would be the map itself at a point, because it doesn't get any better than this. And in fact, this is true. Namely, so basically sanity check, because this shows that our definition of differential seems reasonable. So this is one more confirmation that this gives you a reasonable result and not something really weird, because otherwise you would really have to rethink our definition. So this map L, then L is differentiable, so everywhere differentiable with dl in the point A, so the differential of A in L in the point A is just L. So differential is linear map from Rn to Rm, which is L also, so this is formally well defined. So this is really true. The best approximation of a linear map at any particular point is the map itself. And this holds for all A in Rn. And actually this is not very hard to prove, because this basically fits in two lines. Namely, if we take some arbitrary point in Rn, Take a look at this equation here, what it looks like. We want to find that this is satisfy this equation, but this is almost obvious because if we take an arbitrary h, we know that L of a plus h, which is the left-hand side of that equation here, if we start with this, we know the map is linear. So by linearity, so L linear, by linearity, this is the same as L of a plus L of h. Okay, now this almost looks like this equation here because this, instead of dfa, we have the map L there, which is linear. That's fine. But now there's this phi missing. But it's not really missing, it's just 0. So we can just add the 0 map here. And if you take a look at this equation here, and at the property, sorry, at this defining property of the map phi, if phi would be just the 0 map, this would hold definitely because everything would be 0 here, so the limit would be 0 as well. So we can just put phi equal to 0 and dfa equal to L, and we've got just exactly this equation that we want. So by definition, hence, with phi equal to the 0 map, L is differentiable in A, and it really holds that L has this role here, dLA is L. And that's it. So the best approximation of a linear map by a linear map is the map itself. Good. So our notion of approximation is nice. The next thing is another sanity check, because this is something that we would also expect but haven't seen yet. But since we know that we can use partial derivatives and partial derivation rules there to establish some rules for the differentials, it's reasonable to expect that some of the rules that we already know or some elementary stuff might also translate to the higher dimensional case. And also we would like derivatives or differentials to behave well with respect to our intuition, obviously. And it turns out they are really quite well behaved, so to say. Namely, Theorem 1223. So again, we have M and N in N. Now we take an open subset of Rn and assume we have two maps from U to Rm, and that both of these maps are differentiable in a certain point. Both differentiable in a certain point A in U. Okay, then we have two very elementary properties. First of all, if f and g are differentiable, then their sum is differentiable. The sum is, of course, the sum of vectors here, so pointwise the sum in Rm, meaning so f plus g, which we have already defined there, so already defined earlier, from U to Rm. So we're just adding pointwise. This is differentiable. We have seen before that it's continuous, but now it's also differentiable in A. And the differential of the sum is the sum of the differentials. Okay, with d of f plus g in the point A is just dfa plus dga. The sum of linear maps, and we know that the sum of linear maps is linear. So this is really a linear map, and thank God it behaves well. So because when we consider derivatives in the one-dimensional setting, we always knew that the derivative of a sum is the sum of the derivatives and so on. So it behaves as simple as it gets with respect to sums, and here we've got the same thing as well, so there's no further complication due to sums. Good. Now, this tells us that sums are, no problem for differentiating. And the second thing is then scalar multiplication. Namely, if we take just the map lambda f, so lambda times f, just multiplying with some constant number lambda, which is again a map from U to Rm, again by multiplying pointwise with the scalar, then this is differentiable in A. In A, and the differential of lambda f in the point A is just lambda times the differential of f in the point A, and this holds true for all possible lambda in R. Okay, so there as well. Before, in the one-dimensional setting, we know that multiplying with constants stays just the same under differentiation, so nothing happens. And this is precisely the same for higher dimensional differentials here. So we can just ignore constants, basically, if you multiply with them, which is good. Now, these were the simple things, and now let's consider the proof. And I will only consider the proof of part A, because part B is proven by a similar method, and it's really not that exciting because it's quite technical. Now, for part A, we assume that both are differentiable, so by assumption, there exist maps phi1 and phi2, one will be for f and one will be for g, from U prime to Rm, where again U prime is defined as the set of all h, doing the shorthand notation here, such that A plus H is in U. So phi1 and phi2, such that f of A plus H is equal to f of A plus df A of H plus phi1 of H, and limit as H goes to 0 of 1 over the norm of H times phi1 of H is 0. And the same thing for G and phi2. G of A plus H is G of A plus dGA of H plus phi2 of H. And here limit of H goes to 0 of 1 over the norm of H, phi2 of H is 0. And the idea is very simple. To show that the sum is differentiable, we just add up these two equations. Namely, then, if we take f plus g of A plus H, this must be on the left-hand side of the differentiability equation for the sum. So this is by definition just f of A plus H plus G of A plus H, which is the sum of the left-hand sides of these two equations. So if we replace them by the corresponding right-hand sides, we get f of A. So let me just reorder the terms already. And from the other one, we get G of A plus df A of H plus dGA of H plus phi1 of H plus phi2 of H. So to summarize this, this is f plus g of A plus dfa plus dGA of H plus phi1 plus phi2 of H. Now, this looks like the thing we want for our differentiability relation. So this is the sum of two linear maps. So this is a linear map. So the only thing that remains to be shown for such an equation to hold is that this here again has this property that the limit vanishes. So the limit of 1 over the norm of H times this vanishes. But this is clear since we already know that these two guys vanish. Since if we then compute what we have to show, so 1 over the norm of H times phi1 plus phi2 of H, and if we now pull these two apart as a sum and just multiply each one individually, this is the same as the limit as H goes to 0 of 1 over the norm of H phi1 of H plus 1 over the norm of H phi2 of H. And keep in mind, just in case you're wondering why I'm always writing these in front instead of a fraction, technically this is a number, so a scalar, and this is a vector. So I'm just trying to be consistent with the notation. But so we have just reformulated this as this, and we have known, so by assumption this goes to 0, this goes to 0, so the sum goes to 0. So this limit is 0. And since this holds, this shows that f plus g is differentiable. Is differentiable in A, and the derivative of f plus g in A must be the linear map which stands here, which is nothing but dfa plus dga. Okay, this proves part A, and yeah, B analogously. Very similar, we just take the corresponding equation. This time we only have the first one here, multiply everything by lambda, and then have to show, or basically the only argument we need is if we take lambda times phi 1, if this goes to 0 and we multiply everything with lambda, it will still go to 0. So we will have the same relation there by just multiplying this first equation by lambda. So this shows the claim in the same way. Okay, this was the most elementary part. So basically these two theorems show that the derivative behaves in the way we would, or the differential behaves in the way we expect it to behave, which is good news. But to get some more, and this also tells us basically that we can use some elementary, very intuitive differentiation rules here in multi-dimensions as well. But to do some more, we of course need more rules, namely a generalized product rule and a chain rule. And yeah, let me erase the blackboard and then we will go through these more elaborate rules. Next up is the generalization of the product rule. Please recall if we had in the one-dimensional setting two maps on an interval which were both differentiable in the same point, then f times g, so the product of the two functions, is differentiable on that point again, and for the derivative there is a nice formula. The same thing holds here in the multidimensional setting, but we have to pay attention because we cannot do general maps Rn to Rm because we don't have a product in Rm. So multiplying only works if both maps map to R, to the real numbers. So we have to really restrict to that particular setting because simply we don't have a product otherwise. So in this case we take n in n, we take U an open subset of Rn, and we take a point A in U. If two functions fg from U to R are differentiable in A, then, and now since they both map to R, so this is here important, f times g, which is also going from U to R, this is also differentiable in A. And the differential satisfies the basically completely analogous rule to the product rule we had before in the one-dimensional setting. The differential of f times g in A is now the differential of f in A times g of A plus f of A times the differential of g of A. Okay, and if this looks confusing to you, df and dg are linear maps, and these two expressions here, here's the fixed point A included there, so these are just numbers. These two are real numbers, and so we multiply just by a scalar. Here we multiply from the right-hand side, which is of course the same as from the left-hand side, but I've drawn this in this way so that it really looks precisely, or almost analogously to the formula we had before. So this is this, and just to clarify, if we insert a vector now, so these are linear maps, so we can insert a vector, so f times g a. So in this map we can, let's maybe put parentheses around this, not to be precise, of v. If we insert a vector v now, this would mean, so here we have the map multiplied by something, so this is dfa of v, which is, this is now a real number because, so v is, this is, df and dg are linear maps now from Rn to R. So these are in fact numbers that are put here. So we can multiply this with g of a. And here we have f of a times dg a of v. So we just insert the v into these two d's here and into these two maps, and the rest is just constant. So this holds for all v in Rn. Okay, the proof of this. Sorry for the cut, I almost skipped a part of the proof. So, we know that f and g are differentiable, so we can do the same as in the proof for the sum before, namely by assumption. There are maps phi 1, phi 2. This is really exactly the same as before, from u prime to R this time, where u prime is again the set of all h in Rn. such that A plus H is in U. Whoops. Okay. So that f of A plus H minus is equal to f of A plus dfa of H plus phi 1 of H, and in the same way g of A plus H is equal to g of A plus dga of H plus phi 2 of H. And we have the limit as H goes to 0 of phi 1 of H, and this time I can write it as a fraction because this is now a map going to R this time, divided by the norm of H, is the same as for the case for phi 2, so let's just write phi I. This is 0 for I in 1, 2. Okay, so before we consider the sum of these two and use this to compute the differential of the sum, now we have the product, so we just have to take the product of this. And as you can tell, we have a product of a sum with three summands with a sum of three summands. So there will be quite some summands, and we basically have to show that most of them are not important very roughly. That's the strategy of proof here, and I will not go into every single detail of this. So we derive. So we need to study f times g of A plus H, and to show that this satisfies the equation we want. So let's first find out what we have. So f times g of A plus H is, of course, just by definition, f of A plus H times g of A plus H. So let's replace them by the right-hand sides here. So this is f of A plus dfa of H plus phi 1 of H times g of A plus dg of A, dga of H plus phi 2 of H. Okay, now there's no way around this. We have to multiply this. Just keep in mind this product makes sense because these are all maps going to R, so we have this product. Okay, let's check. So this is the same as f of A times g of A, which is good because this is what we would want to have on the side. This is the same as f times g of A, so this is what we need on the right-hand side of our equation for the differential. This would correspond to the summand here. And now let's see what we have with the df's and the dg's. So first of all, we get dfa H times g of A. So then we get, if we now multiply this with g of A, we have phi 1 of H times g of A. So now we have multiplied everything with g of A. Then we get, so we have to now multiply everything with this one. So we get f of A dg A of H plus dfa of H dga of H plus dfa of H times phi, wait, what did I do? Phi 1 of H times dg, phi 1 of H times dga of H. And now this doesn't fit in here anymore, so let me maybe squeeze that into this box here so I don't have to put this on the next blackboard, which would be even worse, I guess. So here we continue here, and for the remaining part we just need to multiply this with these. But this one, maybe let me summarize this in one term because this is really not important. This is phi 1 of H times, and now let's just write down everything, g of A plus dga of H plus phi 1 of H, phi 2 of H. So I'm just squeezing this because this is rubbish anyhow, I will explain to you in a moment. So let's take a look at what we have. So we've shown f times g of A plus H. So which ones do we need? We first want this one here. F of A times g of A is the same as f times g of a plus, and now let's take a look at what we claimed here. So we claimed that these two form the differential, and as we see, both of them are included there. So one of them, let me take some colored chalk. So this is the one we already saw. Then we want to take these two which form the differential, which is this one and this one here. And we've got a lot of rest. So most of them involves phi 1 or phi 2, so some rubbish function. And this product here, which we would have to tackle separately. But let's summarize this, because we can just write down this is f times g of a plus dfa of h g of a plus f of a dga of h plus phi of h, where we just call phi to be the rest. So where phi of h is defined as all the remaining stuff, which is, so phi h 1 of h g of h actually doesn't matter. So which one? Yeah, plus dfa of h dga of h plus phi 1 of h dga of h plus this part there of g of a plus d ga of h plus phi 2 of h. Yeah, okay, this one, wait, here this was too much. Sorry about that. Okay, but this is just some map. So this is actually of the form we want, but we need to show that this phi really has this rubbish property. So that this really, we need to show in this situation that the limit as h goes to 0 of phi of h divided by the norm of h, that this indeed equals 0. And this is what I will not do here in class. If we take a look at what these terms are, almost all of them are just either contain phi 1 or phi 2 or even both. So, parentheses missing. Here we can basically use this vanishing property of phi 1 and phi 2, so the analogous property here for these two functions, and compute a bit around and use this property to see that the corresponding summands vanish if we just divide everything by the norm of h. The only interesting thing would be this one, and for this we just need a property. We have seen that linear maps are continuous if and only if there's this inequality that the differential or the linear map of h would be small, the norm of a linear map of h is smaller than or equal to a constant times the norm of h. This is only the characterization of continuity for linear maps that we had. And this is what we need to apply for this term and do a little bit of dirty analysis here. So really some dirty computations and inequalities. So this is, I will spare you because the details are really not that important and you really don't need them. So this is contained in the lecture notes. But the main idea is really we write something until we get the differential we would expect and then show that the rest is rubbish. Okay? So this is the idea here. And in the lecture notes, I've really written a complete detailed proof of this. So in case you really want to see the details there, which is also really interesting to learn the techniques from analysis or to repeat techniques from analysis basically that we did in the last semester, just take a look at the lecture notes. Okay. So this was the product rule, and let's maybe do an example of this. So yeah, let me, first one remark. So we have seen that the differential has this property, and this already gives us also a nice formula for the partial derivatives in this setting. So in the situation of that theorem, so everything's defined as above. Whoops. Sorry, horizontal spacing. I'm sorry about that. In the situation of theorem 1224. So how can we get the partial derivatives? If I would have an audience, I would now ask what was again the relation between total differential and partial derivatives. The answer is we just have to insert the canonical basis vectors, so the EI, to get the ith derivative. So if we have the ith canonical basis vector here, we have it here and here as well. And if we then rewrite everything by as partial derivatives, we get that So the ith partial derivative of f times g in the point A. So this would be inserting the ith canonical basis vector there. Tells us that we get, so df of the base vector, so the ith partial derivative of f in A times g of A plus f of A times the ith partial derivative of g in A. This looks a lot like our one-dimensional product rule. So this works in the same way as the one-dimensional rule before. We just have to kind of, since partial derivatives are formed by just deriving everything by the same variable and keeping the rest constant, this really helps us in, so this really is something that works precisely as in the previous semester. So if you could derive one-dimensional functions, you can also derive functions in these multivariables for these products. Let's do an example anyway. So example 26. Namely the following, so let f be a function in two variables from R2 to R, and I will now start calling these variables x and y instead of x1 and x2, but still denote the partial derivatives by d1 and d2, but I hope this is not giving any confusion, but this is usually a bit easier to memorize and to write down. Because the formulas get a little simpler, I'd say. So I take e to the minus x squared minus y squared times the sine of x, y. Okay. Here we can check that the partial derivatives there all exist and are well defined. So for these two factors here, so for these two functions, so we can, maybe let me be precise. So f is g times h, where g of xy is e to the minus x squared minus y squared, and h of xy is the sine of x times y. And we see that g and h are partially differentiable. These ones we have already studied actually. I had a map where I had these two functions as components. There we have seen that. So these are partially differentiable with the following partial derivatives, and let us just compute them explicitly. d1 g in xy, so the derivative of this function by x, this gives e to the something remains, and we get as a derivative of this inner function, we get minus 2x, e to the minus x squared minus y squared, and the same way for the second variable. So if we take the partial derivative, the second partial derivative of g in xy, we get minus 2y, e to the minus x squared minus y squared. Let's do h in the same way. d1 of h, xy. So the inner derivative is then y, so y times x. Y is a constant now if we just consider the first partial derivative. And the exterior derivative would be this of the sine would be the cosine. So we get the cosine of xy for the outside function, and for the inner function we get the derivative y as a constant. Y times x derived by x is y. And analogously, d2 of h of xy is, and now it's just the same with the variables reversed, so we get x times the cosine of xy. So all of them are obviously continuous, So by the previous theorem, we have continuous partial derivatives. This implies that, do I have a number for the theorem here? No, unfortunately not. But by this theorem that we had, that continuous partial derivatives implies differentiability. So we get that g and h are differentiable everywhere. So by the previous theorem, Theorem 1224, our product rule, this first of all said that then h is differentiable. And we compute, and now I need to erase, and then I will compute the differential of this map H using these results. So using these formulas for the partial derivatives and knowing that we have the differentiability of the function f of the product here as well, we can now use this formula from the previous remark to then compute the partial derivatives of the map f of the product of the two functions. Namely, by this remark, this says that so the first partial derivative of f in a point xy is the same as d1g xy times h of xy plus g of xy times d1h of xy. And now we just have to insert the definitions here, and then we'll find out that this is the same as so. Here we had this derivative was minus 2x e to the minus x squared minus y squared times h, which was just the sine of xy. And here we have e to the minus x squared minus y squared, and here the derivative of that, which is y times the cosine of xy. So, yeah, putting things together, we can, yeah, this is the same as e to the minus x squared minus y squared put in front, and then we have minus 2x sine of xy plus y times the cosine of xy. Okay, and in the same way, we get that the second partial derivative, d2 fxy, let me just give you the final result, which is computed precisely the same way. Here we have, again, e to the minus x squared minus y squared in front, and then minus 2y, and now basically just the variables, because this is kind of, both functions are symmetric in the variables, so to say, so this just the variables change their places. So here we have minus 2y times the sine of xy plus x times the cosine of xy. So for the differential, this means, so how is the differential related to the partial derivatives? This is also something you just have to imprint it in your brain, so to say. df, this is now a linear map, so df in the point xy. This is a linear map from R2 to R, so if we insert an element of R2, so a vector which we call by components as v1, v2, this is now by this formula from corollary, do I have it here? Unfortunately not, so but you have a previous corollary where we saw that a differentiable map, there we can always compute the differential by the partial derivatives, and this is the crucial part here. So this is d1f of xy times v1 plus d2f of xy times v2, so all that's left to do is just to put these into the formula. And this gives us, so if we summarize a bit, e to the minus x squared minus y squared. This is in front of everything, so let's put it in front of a big parenthesis. And then we have this there times y1, so minus 2x sine xy plus y cosine of xy times v1 plus this bracket there, so minus 2y sine of xy plus x times the cosine of xy times v2, and now close the big parenthesis. So this is the explicit formula for the differential. A bit tedious to compute this, but the steps we're doing here, it's really not that hard. So it's just putting the right steps one after another, but there's nothing very new because basically we only need the differentiation rules from the last semester and put it all together then in the right way, if we can just memorize the formulas for the differentials. Okay, next up, a chain rule. We have seen a chain rule before, and this is also kind of the rule that's kind of the hardest for someone who's learning this new. So if we had this composition G composed with f, if we had the composition of real functions of that form defined on just one variable, we had that, which we already used here, that we had the derivative of the outer function G times the derivative of the function f at the right points. And now the question is, of course, how does this generalize? Because we can't just multiply because we have linear maps, we have no product. But what would be the analog here? And it turns out the analog is actually quite concise, so it's not that complicated as you might expect. So Theorem 1227, so this is now the general chain rule. So we just need to put in the right setup. So this time we need three natural numbers, L, M, and N. So assume we have U open in Rn, and V be an open subset of Rm. And assume we have a map F from U to V and a map G from V to R to the L. So the composition is well defined. And assume we have a point A in U. And now it's basically the same state of the same assumption that we had in the one-dimensional setting. If F is differentiable in this point A, so is differentiable in A, and now G must be again differentiable, and G is differentiable, and now in which point? In F of A. F of A lies in D, this is all well defined. So there we need that G is differentiable. Then the composition, G composed with F. This is now a map from U to RL. This is differentiable again in A. And so what's the differential? So the differential is the linear map D of G composed with F in the point A. And what is this? Before we had, so in the one-dimensional setting, derivative of G in F of A times the derivative of F in A. And this times is replaced by a very similar thing, by a very simple thing. We take the differential dg in the point F of A. So this is now the point here in the index. So this is a linear map from Rm to Rl by construction. And we just compose with this map with the differential of F in A. So this goes, this is a linear map from Rn to Rm by construction. So this here is a linear map from Rm to RL. So the result is again a linear map, and now going from Rn to RL. So we have seen the composition of linear maps as linear, so this gives us a linear map, and so as you can see, we're using tiny bits of linear algebra here and there. But this is not really the construction here, we just have to take the composition of these maps. And this is a really simple and beautiful formula. It will turn out, as we shall see in some examples, which I will not carry out in excessive detail, but as we see in some examples, if you do explicit computation with this is not that difficult, it's just tedious. It can be very long computations, and it can be very elaborate to write simple things down, but anyway. So this is the chain rule, and let us first prove it, and again, similar as for the product rule, I will only outline you how to prove this and to give you the main idea of the proof, and then leave the dirty details to the lecture notes. Okay, so first of all, before we had the differentiability equations, so the defining equations for this, for sums and products, and then just took sums and products of these equations, and we will do a similar thing here. We will really take basically compositions of these equations. And this is a bit more delicate and a bit more complicated than before, but let's go through this one by one. So first of all, by assumption, we know that G is differentiable in F of A. So let's first of all formulate this for G. There exists phi 2 from a set V prime to RL, where V prime is the set of all, now I call them K in Rm, such that F of A, which is now our point that we consider, plus K is in V. Whoops. So G is differentiable in F of A. This means we take G of, and now the point that we're studying is F of A instead of A, plus some K. So I'm just rechristening the H as K here because I will need the H below. So G of F of A plus K is then, just by differentiability, the same as G of F of A plus dg in the point F of A of K plus phi 2 of K. And here we need that the limit, or we know that the limit as K goes to 0 of 1 over the norm of K times phi 2 of K, whoops, this is a bit small, phi 2 of K equals 0. Okay, like this. So this is what we know. Okay, now in particular, for a suitable for H contained in the set U prime, which is now defined as before, namely as the set of all H in Rn this time. Here was Rm, here it's Rn, such that A plus H is in U. So what do we get? Namely, we can study the left-hand side of the equation we need for the differentiability of the composition. Namely, G composed with F of A plus H. So this must be, to show differentiability, G composed with F of A plus differential plus something. So this is the form we want. And we know that, so this is just G of F of A plus H. Okay, problem is this doesn't help us anything because we only have this form, but let's do it artificially in this form. Namely, this is the same as G of F of A plus, and now just take F of A plus H minus F of A. Very artificially and very arbitrary, but let's do this for a second. So then, if we take a look at this, and if our K, which is here, is now just this part, we can apply this relation here, because this then becomes, so G of F of A, okay, plus, and now we have to be careful, dg F of A of, and now this, F of A plus H minus F of A, plus phi 2 of that. So F of A plus H minus F of A. Now, we have to go, so this already looks a bit better than before because we already have this G of F of A, and then we have something which evolves a differential, but of course this is not something which is not linear in H in this setting, so this is not the differential yet. But we haven't exploited yet that F is differentiable as well. Namely, since F is differentiable, so since F is differentiable in A, there exists a map phi 1 from U prime to R to the M, such that F of A plus H is equal to F of A plus df A of H plus phi 1 of H, where again phi 1 is this rubbish function. So limit as H goes to 0 of 1 over the norm of H times phi 1 of H, whoops, is 0. Okay, this is what we have. And just to see how we can use this, we see that this difference also pops up there. Namely, if we just subtract F of A on both sides, then it would look like this. Okay, and so this means this difference here can be replaced by that. So, in this formula, so we started with G composed F of A plus H. Then we had here that this is G composed F of A. Okay, now we replace. This is dg of F of A, dj in the point F of A of dfa of H plus phi 1 of H plus, and now let's leave the rubbish as rubbish, phi 2 of F of A plus H minus F of A. This doesn't matter. Now, dg is linear. So we know that this looks almost like the thing we want. Just this here, this is in the way. But because it's linear, we can write this expression here as the sum of dg on this and dg on this. So here by maybe let's give it a little more space. So here, since dg F of A is linear, this is the same as G composed with F in A plus dg F of A of dfa of H. And now we've got only rubbish left. This is dg F of A of phi 1 of H plus, let's do it the other way. This is, let me write this down. F of A plus H minus F of A. Okay, this is the rest that we have, and so this looks like the thing we want. We want this to be the derivative, or this was the claim here. So if we define this here, so this part, all of this, if we define this by phi of h, this means this is our rubbish function. So we need to show that this is really a very small function. Because if we can show that this has this nice property that it vanishes in the limit if we divide this by the norm, then it shows that this is the defining equation for a differential, and then this shows that this is the differential. So need to show that the limit as h goes to 0 of 1 over the norm of h of this rubbish map phi of h, this goes to 0, so this must be 0, then the claim follows. And this is contained in the lecture notes as well. This is also quite tedious. This is some standard analysis arguments if you're kind of more advanced calculus guy. But this is something you can just read up there and study the details there. It's not that complicated, but these are kind of quite instructive arguments. But there you can just do the computation and see that this is indeed something which is very small. So in this way we can then prove the chain rule, which I will not do here. Okay, and after erasing we will discuss some examples.